electric and magnetic forces. And so basically, 2/3 of the class is going to be on this. We just finished about 1/3 of the class, roughly speaking. And so let's just talk a little bit about some of the things that are in that handout that I gave you. First of all, charge is quantized. Okay, and so we have mass and we have charge. And it turns out that there's a very similar relationship between the forces of particles of mass and the forces between different types of charge. So electric forces are produced by stationary charged particles. And the basic rules we have are that like charges repel, and unlike charges attract. So this seems pretty obvious and maybe kind of elementary to say this, but it turns out that if you use these important facts, you can make life so much easier for yourself just by realizing that like charges repel and unlike charges attract. It is going to simplify so many calculations that you'll be doing, because you can always break it back down to force relationships where you already know what the answer is. Okay? And so this may seem just overly simplistic to even make a big deal about this. But this is a little different from gravitation, because there's no gravitational repulsion unless you could have negative mass. Okay, then you could have anti-gravity. And there is some indication that negative mass does exist somewhere in the universe, but that would repel positive mass. So this would be a form of anti-gravity. But this is an exotic idea. Not necessarily non-existent, though. When we look at the universe as a whole, it appears, and this was discovered back in the 1990s, it appears as though the entire universe is repelling at very large distances, what's called dark energy. And so this is an anti-gravity effect that seems to be occurring at very large distance scales. It's completely unknown what the physical mechanism is for it. But we don't want to completely rule out the possibility that you could have repulsive gravitational forces. So this makes it a little bit trickier than just our regular masses always attract type of thing. We have M1 and M2. We learned before that the force of attraction is our universal gravitational constant times the product of the masses divided by the distance squared, where r is the distance between the centers of the masses squared. G is our universal gravitational constant, not to be confused with little g, which is the acceleration due to gravity. G is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. So it's a very small number. And so electric forces then are produced by charged particles. Now it doesn't mean that the charged particles can't be moving and still exert a force. What I'm saying here is that the motion of the charged particles is not required. For electric forces to happen. have moving charged particles that are feeling forces. But just like with gravity, you can have stationary masses that are being attracted toward each other. They could be moving and still be attracted. But the motion isn't required for the attraction to take place. There's nothing in this expression that has velocity in it. Now, why am I making such a big deal about that? Well, because magnetic forces require the charges to be moving. So if there's no motion, there's no magnetic force. So something's got to be moving for magnetism to happen. That nothing is required to be moving for electric forces to happen. Now, I'm not going to do much with magnetic forces for at least a month, maybe even a little more than that. But I wanted to compare and contrast them here before we go into more detail with the electric forces. Any questions, sir? Okay, so when we say charge is quantized, it means that it comes in elementary chunks. You can't just break a charge down infinitesimally small. If you keep taking apart charges and pulling them apart with little tweezers, you get to a certain point where you can't go any farther. And so our elementary charge is the charge on an electron. That's minus 1.6 times 10 to the minus 19 C, where C is our unit for Coulomb. And the charge on a proton plus 1.6 times 10 to the minus 19 coulombs. Okay, so the elementary charges are equal and opposite on an electron and a proton, and you don't get any smaller than this. That being said, when we get to 208C, we'll see that quarks are actually fractional units of electric charge, but they can only exist in combination with each other within the nucleus. If you try to take quarks and pull them apart, you add so much energy to the system that you just create more particles, but you don't get free quarks, unless maybe in the very early universe when there was just 100 zillion, quadrillion degrees, maybe you could get what's called a quark-gluon plasma at that time. But in the present-day universe, it's impossible to make free quarks. And so this statement in our present-day universe is a correct statement, even though we do know from theory that there are fractional units of the electric charge that make up the proton and the neutron that we call quarks, that we'll talk about in 208C. Okay, and so the mass of an electron is about 1/2000th the mass of a proton. So even though the charges are the same, the mass of an electron is about 9.1 times 10 to the minus 31 kilograms, and the mass of a proton is 1.67 times 10 to the minus 27 kilograms. And so if we take the ratio of these, we get 1836, or almost 2,000 times more mass for a proton than an electron. So protons tend to be the heavyweights. They have much more inertia. Electrons are the lightweights, but they both feel the same force, F equals ma. So in one case, F equals the mass of the electron times the acceleration of the electron, and in the other case, the force is equal to the mass of the proton times the acceleration of the proton. But the forces that are electric, at least, are equal because there's equal charges. And so what that means then is that the protons are like big diesel trucks, and the electrons are like little VW bugs driving around. And so if you had a big diesel truck moving along, and then a VW bug comes along, gets in front of it, feels a little jolt, looks around, doesn't see anything. The little car is knocked 2 blocks away, and he just keeps going. Hardly moved him at all. But there was a huge acceleration because there was a smaller mass. So the electrons then, as they're being transferred from one place to another, are responsible for most of the charge differences that we see. So we get a net charge on an object either from taking away electrons or by adding electrons to an object. And not by adding or subtracting protons. That would make it more negative. Or subtracting electrons. Which would make it more positive. So we don't want to ever, when we see something as a positive charge, we don't want to think about it as having more protons. We want to think of it as having less electrons. In most situations, where we're dealing with large quantities of matter. There are situations where you're just dealing with subatomic particles, but for the majority of the situations we'll be looking at here, it's the electrons that do all the charge transfer. Now when we look at the force between 2 charged particles, it also obeys an inverse square law. So this is our force of gravity. This is Newton's inverse square law. So remember that in Newton's inverse square law, if you double the distance, what does that do to the force? 1/4 as big, because it goes like 1 over 2 squared. If you triple the distance, 1 over 3 squared. If you quadruple the distance, 1 over 4 squared. 1/16, etc. Same thing is true with electric forces. Very similar thing, the G is replaced by a K. We call this the Coulomb constant. K is 9 times 10 to the 9 Newton meters squared per Coulomb squared. So we look at that, we go, oh, well that looks kind of similar. And then we have, instead of masses, we have the product of the charges divided by the distance squared. So here's our charge Q1. This is our charge Q2. This is the distance between them. Let's say that they're both positive. Then we're going to get forces that are going to be repulsive. But they'll be equal and opposite, because for every action, there's an equal and opposite reaction. So the magnitude of F1 is equal to the magnitude of F2, but they're going to be in opposite directions. Remembering that Newton's third law is for every action force, there's an equal and opposite reaction force. Okay, so we see something that looks really similar if we just make these substitutions. Then mass goes to charge, and big G goes to K. But one thing that we'll notice here is that K is 20 orders of magnitude bigger than G. And so that means that if we were going to look at the forces between, say, a proton and an electron, there were electrical forces, and then compare those to the gravitational forces, we could be dealing with a difference of maybe 10 to the 30th power difference between the electric forces and the gravitational forces. And somewhere in here, I did a calculation like that. The handout that I just gave you today. If we have, let's do this for 2 protons. Okay. This is the force between 2 protons. We do this for the force of gravity. That's g times the mass of the proton squared, m1 times m2, because we have 2 protons, divided by the distance squared. And so let's make that distance 1 meter. That's what I did in this example. And I get the electric force, the gravitational force in this case is going to be 1.86 times 10 to the minus 64 newtons. We do this for the electric force, this up top here. Then at a distance of 1 meter away, k times q squared over r squared. And so that's going to be the charge on a proton squared. So that gives me 2.3 times 10 to the minus 23. So when I take the ratio of those two, we see that the electric force between 2 protons at 1 meter's distance is 10 to the 30th power bigger, because of the fact that k is so much bigger than g. So we might wonder, well, why is that? Why would the gravitational force be so weak? And, well, these are just measured values, so we can't be sure. But there is one theory that kind of goes along with multidimensional spaces that speculates on the possibility that gravity, we live, say, in some kind of a string theory environment. Maybe string theory isn't the right theory, but something that's like that, in which the gravitational fields or forces can sneak out through higher dimensions, but the electric forces stay confined within our 3-dimensional space. So the gravity forces are leaking out, and that's why the electric force is so much larger than the gravitational force. That may or may not be true. That's just one theory to try to explain a mechanism for why there would be such a big difference between the electric force and the gravitational force. But just to further clarify this, let's say that we could take a speck of dust and remove all of the electrons from it, just a tiny little speck of dust. Then another little speck of dust there, and take away all the electrons. It'd be way smaller than that, right? You can see this. You can't see a speck of dust in the front of the classroom. But you remove all the electrons, and then you figure out the gravitational force, insignificant. But the electric force, F, is something like 10 to the 7th power newtons. Something like 10 million newtons of force, which is millions of pounds worth of repulsive force, just from 2 specks of dust. Okay? And so this is what gives us an idea as to how much stronger the electric force is than the gravitational force. So Fe then is much greater than the gravitational force. So it wins. And what this implies then is that electric forces dominate at molecular distances. And so in other words, all atoms are held together by electric forces. That's the source of the binding force between atoms to form molecules. These molecular bonds are almost completely electric force related. And so if you want to determine whether an atom is going to become a molecule or not, it's a relatively simple process of just seeing how much positive repels how much positive, and then how much negative attracts how much negative. So you look at all of the positive and negative forces in an atom, and you add them all up. So the attractive forces are between positive and negative. And the repulsive forces are between positive and positive and negative and negative. And so conceptually, it's an easy process. Now, actually doing the calculations isn't easy in many situations. But the idea is very simple. If the attractive forces are greater than the repulsive forces, then we have a molecule. But we just have monatomic if repulsive forces are greater than the attractive. So an example of something that's monatomic would be helium. If you take a helium atom, you add up all the attractive and repulsive forces, you end up with the repulsive forces with. So you don't get a helium-2 or a helium-3, or you can get liquid helium at very low temperatures, but that's a completely different kind of quantum mechanical and isn't related to what we're talking about here. Whereas with hydrogen, when you have an electron that's between the two, there's going to be 4 times the force on the negative and the positive as there is between the positive and the positive. And that more than makes up for the lower amount of force when it's out here. So when you add this all up, because of the inverse square law, the binding forces win, and so you have the H2 molecule. Okay, and so that's the basic idea then when we're interested in the electric forces. It's when we are studying atoms and how atoms can form into molecules on that kind of a size scale. On the other hand, on larger size scales, it's gravity that dominates. So if we want to look at the forces between galaxies, or even the force of the Earth going around the sun, gravity wins. And so how could that be true if the electric forces are so much greater than the gravitational forces, and they both obey the inverse square law? Yes, but why? The mass is, well, if we looked at the difference in force, so that here included the mass when we were doing the gravitational relative to the charge, and we got 10 to the 30th power bigger for the electric. So what's changed when we go to greater distances? What?
R distance.
But it's the inverse square law for both of them. The mass is associated with each charge. You still have the same amount of mass and charge in each individual atom, right? So what is it that's different on a large distance scale?
Because larger masses generate their own electric field.
Well, that would go, that would argue against, not for it. That would argue for electric fields being significant at large distances. The electric fields are negligible.
Larger masses tend to have a more net neutral charge.
Good. neutral charge on a large object. You don't, when the universe was created, it was created with equal numbers of protons and electrons, we believe. And at first, they formed mostly into hydrogen and helium, which had mostly the same electron and proton numbers. And so when you take a large aggregation of matter, the charges cancel. So does that make sense? The charges are going to cancel because the Earth, say, has 0 net charge. But it still has mass. So the mass wins by default. But if the charges cancel in a large object at great distances, then why don't they cancel at small distances? We still have equal amounts of charge. K was always the same value whether it was a big object or a small object.
Because there's not that many, objects per se, or molecules or atoms. There's less at small distances.
They what?
There's less particles at small distances.
Okay, there's less particles at small distances.
So there's less interactions that cancel out. They don't cancel out because there's not enough charge.
Okay, well let's look at this for a second. Let's look at you're really far away from, let's say you're just dealing with a positive and a negative charge. This is called a dipole. You have a positive and a negative charge. Let's go along the axis of the dipole, and let's go way out here to infinity, or maybe Mars, okay? Just really far. And then let's look at the way that the forces add up. So if we go way out here, and then let's say we have another positive charge. Okay, so that's going to have an attractive force toward negative, and a repulsive force away from positive. So this is where drawing your vector diagrams is super critical, that you understand that like charges attract, unlike charges, or like charges repel, unlike charges attract. Okay. So here, I'm drawing this force as being an attractive force between the positive and the negative, but I'm drawing this one as being a repulsive force between positive and positive. So now let's move away out to here. Can you see that in the limit, as we get very, very large, the two forces become anti-parallel? So the forces then cancel at great distances because they become anti-parallel. What about the gravitational forces? Those are still going to both be attractive. So we have a surviving gravitational force, even though the electric forces have canceled. Fe1, Fe2. They're essentially anti-parallel in the limit as this angle goes to 0. Right? And so essentially, it's treating them as if they're in the same location for great distances. Now what if I come in close? If I come in close, then this positive repels that positive. This negative is attracted to that negative, and so we have a net force. Because the two force vectors are no longer anti-parallel. And they actually reach a maximum value when it's halfway in between, because then it's going to be repelling the positive and it's going to be attracting the negative. And so that's the reason why gravity wins at large distances. So at large distances, the electric forces, although they're 10 to the 30, they're still 10 to the 30th power stronger, but they're exactly anti-parallel. And the gravitational forces win by default because they're not canceling. They're adding together. It's as if you had a mass that's right in the center here that's twice as big as either of these two masses were. Okay, so I'll be doing some math with that in a little while, but I don't want to get too far ahead. But that's a good conceptual question that I've asked before on quizzes and exams. Are there any questions about that? This would be the gravitational, so these are the electric, and these would be the two gravitational forces. Now they might be 10 to the 30th power smaller than the electric forces, but they're pointed in the same direction, so they add together. And these forces become, in the limit as theta goes to 0, becomes exactly anti-parallel, and so completely cancel. So then the gravity wins by default.
Those two gravitational components would also be parallel to each other?
Yes, they would be parallel, and so that's what I meant when I said it's equivalent to the two masses being combined at one single point here in the center. You know, in the limit as you get far enough away, so that this distance is completely negligible in comparison to that distance. Question?
It's because their x vectors cancel out, right?
Mm-hmm.
Just because they're exactly the same.
Right. And the gravity forces x vectors add. All right, so with that in mind, let's move ahead and start looking at some simple calculations for electric forces. I'll come back to the dipole problem and actually put some numbers on it a little later. Why are we interested in dipoles? Well, because it's a separation in charge that produces electric forces within atoms to form molecules. And so it's one of our critical, most important applications of electric forces. Now what about if we get smaller than an atom? Well, if we get smaller than an atom, then the electric forces within the proton and neutron of the nucleus become super big, that it still holds together. And so the reason for that is that there's even a stronger force at shorter distances, called the strong nuclear force. That's like little short-range hooks. They're even stronger than these electrical forces when the two charges are almost on top of each other. The strong nuclear forces combine together the nucleus. So electric forces don't dominate at this scale of subatomic, but they do at the molecular level, and then gravity takes over at the larger scale. All right, next, let's just take a look at two charges, plus Q, plus Q, and let's say that this is charge 2, this is charge 1, this distance r, let's say, is 1 meter. I'll use 1 meter a lot in these examples just because it makes the numbers easy to work out, so I don't have to use my calculator as much. And so for this problem, let's say that the magnitude of Q1 equals the magnitude of Q2 equals 10 to the minus 5 coulombs. So in part A, let's figure out how many electrons were removed from each of these objects. In order to produce this charge, we call this 10 microcoulombs. 10 to the minus 5 coulombs is 10 times 10 to the minus 6 coulombs, which is 10 microcoulombs, where a microcoulomb is 10 to the minus 6 coulombs. Now, why are we using coulombs, by the way, if the number of these protons or electrons is so huge? I mean, the numbers are so incredibly small for the charge. If the charge on an electron is 1.6 times 10 to the minus 19 coulombs, that means that it must be a gigantic number of electrons to make 1 coulomb. Let's do that calculation first. How many electrons in a coulomb? See if you can do that, just real quick. Just from what we talked about here. How do we do that? We can say the number of electrons is equal to, and then what do we do with that? How many coulombs? Question mark coulombs. How many people think they have? What did you get?
6.25 times 10 to the 15.
Very good. That's right. How did you get that?
I did 1 over the absolute value of the charge of an electron.
Good. And why did you do 1 over?
Because I wanted 1 coulomb over, however, I wanted to figure out how many electrons there were per coulomb, and the charge of an electron was telling us how many coulombs per electron. So I did the
Coulombs
inverse.
per electron.
Yes.
Right.
So I did the
Okay.
inverse.
Right. So you did the inverse of it because you're looking for a number of coulombs per electron. Okay. Now, one way of thinking about this is, what if this were just 10 to the minus 19? Then how many electrons would be in a coulomb if that were the case? It would just be 10 to the 19, so it would be 1 over that. So it kind of makes sense that it's 1 over 1.6 times 10 to the minus 19. Which kind of seems reasonable. And so that's 6.3 million electrons equals 1 coulomb. That's an incredible number of electrons. So why are we using this unit for charge? Well, because that's typical of the flow of electrons through an electrical device. For example, this monitor we're looking at here might have a coulomb per second worth of charge flowing, which is what we define as 1 ampere. Okay, and so in 1 second then, we would have 1 coulomb's worth of charge flowing. But there's so many electrons that we're using a unit of measurement that's typical of what we would tend to find in normal electrical devices that we use. And so that means that we are talking about an astronomically big number of electrons, and it's hard to visualize big numbers like that. And so we use a unit of measurement that's more natural to the type of problems that we're going to be solving, which would be circuit problems which deal with amps and ohms and volts and things like that. And then we can always go back, though, and realize how many of these little electrons that corresponds to. They're just huge numbers. Okay, so if that's the case then what about 10 to the minus 5 coulombs? How many electrons are removed? 10 to the minus 5 coulombs, and 1 coulomb is this, then what's 10 to the minus 5 coulombs? Isn't that what we're talking about? Just dividing that by 10 to the 5, 100,000? So that means that number of electrons here would be 6.3 times 10 to the 13th power electrons. Are they added or removed?
Half are removed from each. Oh, never mind.
Half are removed? If each one has the same charge, are we removing half from each? No. We're removing 63 trillion electrons from this one, and we're removing 63 trillion electrons from this one. So that's how we get that charge then. We're not adding or subtracting protons. The protons are like big diesel trucks because there's a difference of 2,000 times the mass. That means the electrons accelerate 2,000 times greater given the same electric forces. So the electrons do almost all the moving. Okay, so we've got that. Now let's next figure out what the electric force of repulsion is. So that's going to be our K, 9 times 10 to the 9, Newton meters squared per Coulomb squared, times the product of the charges, that's going to be 10 to the minus 5 coulombs squared. Remember, it's K, Q1, Q2 over R squared. So Q1 and Q2 are equal to 10 to the minus 5. Then we'll divide that by 1 meter squared. So that gives us 9 times 10 to the negative 1. Here's 10 to the 9, here's 10 to the minus 10, right? So that would be 0.9 what? Newtons. Good. Okay, so how do we get units here, Newton meter squared per Coulomb squared? Well, the units for force is newtons. The units here of Q squared over R squared is Coulomb squared over meter squared. So in order to Newton, this is Coulomb squared over meter squared. So this has to be Newton meter squared over Coulomb squared. So we can cancel out the units and get newtons equals newtons. And so that's what the proportionality constant always does, is it just makes the left-hand side of the equation and the right-hand side of the equation dimensionally consistent. And so we use the proportionality constant as our catch-all to absorb all of those units and make sure that the units on the left equals the units on the right. And so our answer then is 0.9. So it's going to be 0.9 in this direction for F2. But it's also going to be 0.9 in this direction. So we solve two problems at once. Now what if these charges weren't equal? Then would we have the same force? Yes, because it's still action-reaction. And so the two forces wouldn't be the same as this value, but they'd be the same as each other. Okay, so that's important to realize, is that Newton's third law is still working. For every action force, there's an equal amount of reaction force. Now, how is this problem going to change if I change Q2 to minus 10 to the minus 5 newtons, or coulombs? And then Q1 is equal to plus 10 to the minus 5 coulombs. Now that's going to be an inward force, but can you see that it'll be the same magnitude as what we just calculated? Because the magnitudes of the charges are the same. So how do we get the direction then? Well, go right back to that original, like, you go, oh, well, okay, I'll make one of these charges positive and one negative, and then I'm going to get a negative force. But this is a negative force going in the negative direction, so therefore that's a positive force. Just positive attracts negative. That's all you need to do. You don't need to think in terms of trying to solve the math here and go through and figure out what a negative force represents in terms of two completely different coordinate systems. That's going to be confusing and unnecessary. Just use the fact that unlike charges attract. And you've got the direction automatically. That's what I mean when I say that this simple rule is going to save you a huge amount of trouble rather than just trying to go in here and figure out what all those minus signs mean. Any questions about that? Okay, so this is where we'll pick up then on Thursday.